Could there be a fundamental hole in science? Is it possible that some of the conflicts we find in the currently accepted physical theories stem from an intrinsic inconsistency in what they intend to do? In my previous videos, I raised the point about self-preference in the application of scientific theories. My intention was, through a simple example, to show how a presumably deterministic theory, Y, applied on a presumably deterministic system, W, can result in an indeterminacy if the theory is implemented within the system. The reason is that a Gödel-like loop can be constructed so that G contains in its input G itself executed inside the system W with the same input. The immediate conclusion should be G does not exist. But you can also interpret that G exists, but at some point it overloads and breaks down, but just as a human tool, because it could be still driving how things work in physics.
You could tell me that I'm already late, since the prevailing theory right now, quantum mechanics, is already non-deterministic. But my aim is indeed to connect to it through this reasoning, and to defend that those loops lie at the root of the measurement problem, or the wave function collapse, if you want to call it like that, and also the correlation of Bell's test and the randomness in quantum mechanics in general. Since its beginning, quantum mechanics has followed the path of undeniable success, but I still think it has left something behind. Something subtle enough as to let it to go forward. But still, sooner or later, there will come things that don't add up. And that's already happening. That's why there is a crisis. Science strives for objectivity, but that doesn't mean it's not plagued by biases. Maybe we are applying our theories, whatever they are, in a way that is ultimately inconsistent, only because we are blinded by our concern of keeping consistency at all costs.
So, how about diving directly into inconsistency and see how far we can get? Later, we might think of finding a way to avoid those gaps. Since we are going to try to build theories about the world anyway, knowing that if we try to make them perfectly consistent, we will bump into inconsistency since it is essential. Why don't think reverse? Let's try to make inconsistency an essential ingredient of our theories. I don't really know how this could be approached,
But I do find myself pitting into a way to reconfigure the base of our current laws so that they must deal with the double conditioning imposed between any system under study and its environment. Or we could say, between our universe, let's represent it as this thing, and one part of it. Let's say it is this isol, and that could be an observed phenomenon or an experimental outcome. If we look back at the essential idea of least action principle, motion is then defined as a balance between them, and it is found through an optimization. But if you tamper a little with the base of it all, there appears a complex cross-influence that I'd like to explain to you very soon, and that makes the situation very hard to solve. What comes different is that not only the quantity for the experiment, delta S1, is the one that must be optimized. The outcome choice should make optimal the whole computation for universe and experiment together. In addition, if our phenomenon, for any reason, starts a mimicking process in its surroundings, and this could be any form of predictive guesswork, correct or not, coming from any element of the environmental setup, then the minimization could get infinite and non-computable. The reason is that the parallel computation also changes action all over and forces the whole system to recompute. The problem must indeed have a solution, which is minimum action, but finding the solution could be unreachable within the system itself. Of course, this action is no longer what it used to be. It will need to be redefined.
This video, together with the other two where I discuss the story of the captain, the spaceship, and the planet, which is in the end an imaginary situation to highlight this inconsistency. Well, they are an introduction to what I really want to propose. And my proposal is that the quantum randomness that's in determinacy we found there comes from this kind of mechanism, through the rule that things have chosen to evolve, action. So this in the end is a return to the old classical least action principle. But if it is so, you'd ask, how come that it wasn't found in classical mechanics in the first place? And well, that's because for this effect to show up, you have to empty your mind of some assumptions that have always been in the basis in which we conceptualize physics: time, space, and matter. But that's the next thing I wanted to tell you about. So see you in the next chapter.